In the previous video, we've used the orthogonality relationships to simplify the formulas, but still the formulas were quite messy and the structure of the formulas is a little bit obfuscated. So this is why we're going to define some new types of matrices to hopefully bring out more the structure of these equations. So we're going to define a certain matrix, which is the overlap matrix between layers in medium 1 and medium 2. And they're defined in such a way that the ijth element of that matrix, by definition, is basically the scalar product of the electric field with index I in medium 1 times the magnetic field with index J in medium 2. And then obviously you can also define its little brother or little sister, which is the overlap matrix from 2 to 1, where the definition is what you would expect, but this time it is the electric fields in medium 2 with the magnetic fields in medium 1. Okay. Question is, with these definitions, can you now pause the video and try and simplify the equations that we had in the last video? Before we do that, a quick recap of the formulas behind matrix multiplication, because they will come in handy. If you have two matrices A and B and you multiply them, and you're interested in, for example, the ijth element of the product of these two matrices, this can be calculated by having a summation over K, where you have I, A, I, K, B, K, J. So this is the definition basically of matrix multiplication. So just if you want to convince yourself of the fact, if you have the product of these 2 by 2 matrices, of course that will result in another 2 by 2 matrix, and you're interested in, for example, this element over here, which is the element in the second row and the first column. The way you get this is by basically multiplying this row with this column over here. So this row here is the second column of this first matrix, and then this column over here is basically the first column of the second matrix. So if you see what's going on here in this product of this guy with this guy, what will happen is that if you want, the outer indices will stay the same. So we have a 2 over here, 1 over there, corresponding to the 2 over here and the 1 over there. And then the stuff in the middle, if you want to call it like this is what's being summed over. So this is exactly what we have here. So this I corresponds to this fixed first index, the J corresponds to the fixed last index, and then we sum over K, which is then making up the indices in the middle here. Okay, but this will come in handy later on. Right, let's copy what we had earlier. So we had the summation over J of, and then let's see what we had. We had the electric field 1I H J 2, okay, plus electric field J 2 magnetic fields I1. This is all copy and paste from the previous video. And then we had TJP, and then in the right hand side 2 times delta IP, and then we have electric field P1, magnetic field P1. Right. So let's see how we could bring in the definition of our overlap matrix here. So this guy over here, this is going to be an element of the overlap matrix 1, 2 here, because the electric field is in medium 1, the magnetic field is in medium 2. And by definition of the matrix, this is the ijth element of that overlap matrix. Okay. Over here, what do we have? Well, this will be an element this time of the overlap from 2 to 1, because the electric field is in medium 2. Which element? Well, we have, if you look at it, we have the j'th element of that matrix. But the j'th element of a certain matrix is the ijth element of the transpose of that matrix. And I'm writing it like this because then this ij here will feel right at home next to this ij over here. Okay. Yeah, and then this thing, tjp, Well, we're just going to define a transmission matrix, which is collecting all of these elements, such that the jpth element of that matrix is just the jp here. So this is just trivially writing this in a matrix form. And then finally, what we have over here, yeah, this is just 1 because of the way we chose to normalize our modes from now on. So this is just 1. But if you then see what's going on here, we have a summation over j. If you combine these two in a single matrix, which is just the sum of these two matrices, then we have exactly the same situation as we had up here, right? So we had a fixed initial index I, then we have a middle indices j over which we sum, and then we have a fixed final index b. So in essence, what we have here is if some sort of matrix multiplication that's going on, namely of the first matrix, which is overlap 1, 2, second matrix overlap 2, 1 transpose times transmission matrix. And I'm focusing here on the ipth element of that matrix multiplication. And then on the right hand side, we have 2 times. Well, this delta ip, if you want to write this in a matrix form, you can say I'm looking at the n by n unit matrix, and I'm looking at the ipth element of that matrix, because this indeed also will give you delta ip by definition of the unit matrix. So what do we have now? We have, in essence, a matrix over here and a matrix over there. And we've said that the ipth element of this matrix is the same as the ipth element of that matrix. And that is basically something that's true for any I and for any p. So in essence, what we have at the end of the day is that these matrices are completely the same. We can say that the transmission matrix is 2 times, and then the inverse of that other matrix, the overlap 1, 2 plus overlap 2, 1 minus 1. And this thing is a lot more compact and a lot less scary looking than this general complicated explicit summation over here. So that's good news. Okay, so now that you've seen this example, pause the video and do the same thing for the expression involving the reflection coefficient. Okay, so what do we have for the reflection coefficients? So just copying the equations that we had earlier, we had that reflection coefficient RIP that was equal to 1/2, and that we had the summation over J of electric field J2 magnetic field I1, and then we had a minus sign electric field I1 electric field J2. Okay, that should probably be right. And then we had the transmission coefficient JB. Playing the same trick over here, this is going to be an element over the overlap matrix from medium 2 to medium 1. And it's actually the jith element of that matrix, or it's the ijth element of the transpose of that matrix. And over here we have the overlap matrix to 1, 2 here, and then this is the ijth element. And then, as we've said earlier, this is in essence the jpth element of that matrix T, which we've defined. So again, we have the product of 2 matrices going on, and then looking at the ipth element of the results. So this is 1/2, and then we have a matrix overlap to 1 transpose minus overlap 1, 2. Okay, taking the product with the transmission matrix, and we're looking at the ipth elements of that matrix. But if these 2 matrices have the same ipth elements for any value of I and P, this in essence means that the matrices themselves are the same, so that the reflection matrix can be calculated by calculating 1/2 and then overlap 2, 1 transpose minus overlap 1, 2. Transmission matrix multiplied by the transmission matrix. Okay, So again, a much nicer looking, much more compact equation that really brings out the structure of what's going on. Okay, yeah, then just to wrap things up and make it a little bit more concrete of how you can calculate the reflected and the transmitted field. So basically the problem that we've been studying so far is we have been exciting the interface with mode, for example, mode with index p. So you can represent this by this expansion coefficient vector where you only have a 1 at index p. So what you construct is a column vector of the exciting field, which only has 1 here for the mode that you're exciting it with. And then what we've been calculating are the expansion coefficients of the reflected field. And this reflected field, these expansion coefficients, you can also collect them in a column vector. So for example, R1p all the way to Rnp. Now, if you look at this guy over here and then the reflection matrix, as we've defined this, another way of arriving at the same values is by taking our reflection matrix, which is a matrix as follows. So we have R1n, and then here for the nth row we have Rn1, and then Rnn. So you can get the same values by, in essence, multiplying it with the column vector that describes the incident field. Because this matrix multiplication, what it will basically do, if you do this matrix multiplication step by step, you will notice that this 1 here will result in picking out the pth column of this particular matrix here. So this really shows you that you can calculate the resulting field by taking the reflection matrix and multiplying it with the vector corresponding to the incident field. This is just for the case where you are having an incidence with a single mode, but you can generalize this by saying that you have an incident field vector consisting of an arbitrary expansion in the different modes of the incident medium. So if you have now an incident field vector consisting of different expansion coefficients A1 from AN, well, then by linearity, you can basically say that this is the reflection coefficient, sorry, reflection matrix times A1 and then 0, 0, 0 over here for figuring out what happens with the particular result from exciting it with first modes. And then we have R, and then we have 0, A2, and so on and so forth. So then you basically have all these guys. And then by associativity, it's basically, again, the same conclusion that you can find the reflected field by taking the reflection matrix and multiplying this with the vector that describes the expansion coefficients of the incident field. So this generalizes to arbitrary incident fields. Also worth mentioning is that you have written down here R. So in essence, what I should have written down is the reflection coefficient if you excite from medium 1 and if you reflect in medium 2. And the same thing, T actually represents the transmission from medium 1 to medium 2. But obviously you can play exactly the same game if you excite from the other side, and then you have another set of matrices. And together, these 4 matrices will completely describe how you scatter at the interface between two different fields. Right. A final thing I want to mention is if you look at the general structure of these equations that we've derived so far, the question is, do they look familiar to you? So pause the video and think, for example, at what happens if you just have an interface between 2 uniform media. See if you can see any similarities there. If you look at the interface between 2 medium, so you have, for example, a uniform medium with refractive index 1 and another one with refractive index 2, and you look at perpendicular incidence with a plane wave, then from basic electromagnetics, you have derived transmission coefficients that look as follows. So 2 times N1 divided by N1 plus N2, and a reflection coefficient that goes like this. Now, obviously, if you compare that to the equations that we had in this general case where the 2 different media were not uniform, Then we had a transmission matrix, which had the following structure: 2, and then overlap 1, 2, plus overlap 2, 1, minus 1. And then for the reflected field, we had 1/2 overlap 2, 1, transpose minus overlap 1, 2 times the transmission matrix. And you really see the parallel in terms of general shape for what's going on here. So here we have, well, the 2 over here corresponds to the 2 over there. If you forget for a moment about the numerator, the denominator is basically the sum of something. And then for the reflection matrix, well, if you substitute t in this equation, then this 2 and this 1/2 will cancel. And then you basically have something which has a difference in the numerator and a sum in the denominator. So it looks very reminiscent of what's going on for a uniform medium. And actually you can even use these particular equations over here, see how they simplify if you have uniform media, and then it will turn out that all of these overlap matrices will basically become diagonal, so there will be no scattering from mode to mode, and then you actually end up exactly with these equations over here. So that's just a nice little parallel I wanted to point out. So by now we know everything what happens if you go from one interface to the next interface. We know the transmission, we know the reflection, so we know completely how this thing scatters. What you then in the end really want to do is build up different layers in your cake and then see how you can calculate the reflection and the transmission matrices of the entire stack of layers. But let's not go so far. This is something that falls out of the scope of this particular book here.